Guys, this is Abhijit. This again is a recording for MSCS METCS 767, and this is the short version. I have a longer version that I've uploaded to Blackboard. So what I'm doing here is this is for my term project. It's basically for quality of wines. I'm using the data set provided by UC Irvine. It has 11 features and one output. The 11 features define various aspects of wine, and the one output defines the quality. At a high level, what I'm doing is I have two Python files. So Python, Pandas, NumPy, Scikit, and TensorFlow were the tools of choice. In the first Python program, I'm basically pre-processing the data. What I mean by that is I get the data into Pandas. I normalize that data, so bring the mean closer to 0, standard deviation closer to 1. I remove any outliers, which means that if there are any outliers for scale, I basically bring them down and scale that data into uniform scale, and then I create bins out of the data, which means that I label them. I create a new label called quality label, and based on the value in quality, I basically label them quality labels, and I call them poor or good. And this is based on if a wine is greater than quality is greater than 8, it's good. If it's lower than 8, it's poor, right? Once this data is generated, I save the file. This is how that file looks like. So all this data is normalized, and then you have the quality label here, and the quality label is later converted again. So once that data is generated, I have my TensorFlow model, and what I'm doing in the TensorFlow model is a few things. One, I can use unnormalized data, or the data that has not been through this, or the data that has been through pre-processing. And the reason for that is basically the outputs are significantly different. So if I run this same model with unnormalized data, I get 100% accuracy, versus if I run it with normalized data, I'm getting only close to like 75% accuracy, and I'm actually trying to see why that happens, right? So I'm actually running the model now while I continue to explain what's going on, right? So here you see 72%, and then I also, like, every run has two runs. One, I run it through a multi-layer model, or I run it through a single layer model, and I'll show you that below. What I'm doing here is I'm basically getting the data, massaging the data. So I'm getting the output, basically wine quality labels in this case, which I created in the pre-processing, and direct quality column in this case. And I'm basically converting into a binary, into a tensor of binary. So 0 if quality is 1 is greater than 7, or 1 if it is less, and again 0 if it is good, and 1 if it is bad. And then I convert that into a 2x2 matrix. So it will convert, zeros will convert to 0 1, and 1 will convert into 1 0, right? Or 1 0 and 1 1. So once that is done, then I take that data, use the train test split library from Scikit, and I split that data into 30% testing and 70% training. I print the sizes here. Again, X and Y will have the same size because it's coming from the same data set. And then once that is done, I set a few key parameters like learning rate, and number of inputs, outputs. And then I have a few functions. This one will basically create batches of the data. This is if you are running a multi-layer model, this is the first layer or the hidden layer. This is the output layer. And again, all it's doing is just making sure that weights are uniformly distributed, or weights are adjusted to get better. This is the training. I'm using the gradient descent optimizer to reduce loss, basically. So it's kind of back propagation, and that's how training is done. This is the function to calculate losses, and this is the function to calculate accuracy, right? And then again, like I said, I have two functions. One is for single layer, one is for multi-layer. And because I had to create those, I basically created a function for run model, which does the other basics. So in the single layer model, you basically have just one layer. So the output layer is basically the input placeholders and number of classifications, and then that will go directly to the output layer, which is here, and it will adjust weights and get you output, and it will run the optimizer here, and it will run the softmax function, so on and so forth, and it will get you the output. Once the output's there, then it will calculate loss, then it will train again, and it will send it to training, and then it will calculate accuracy, and then based on that it will run this model and give you a final accuracy. Similarly, for a multi-layer model, it will go to the hidden layer first, then it will go to the output layer, and the rest of the stuff just stays as it is. A few key things what I found is a learning rate of 0.001, instead of that a learning rate of 0.5 is much better for both unnormalized and normalized data. We are definitely getting much better results using normalized data and a learning step of 0.5. I'm still diving into why that is. Originally I was trying with 20 neurons in the hidden layer, but I found that that's a overkill. I could probably get within the same point difference using 10 neurons, so that's why I've set it to 10 neurons. So these are the two things that I'm playing around with right now. And the other big unknown for me right now, which I'm kind of diving into, is why does the accuracy go up so well when I basically set up when I basically use unnormalized data. Like you can see, it went from 72% to 99%. So definitely there's something that the normalized data is missing, which is getting less accuracy. But that is the other thing that I'm looking into. So this is the 2-3 minute presentation of my model, and of course, like I said, I have a much deeper and a much bigger presentation that I've uploaded to Blackboard. Thank you.